The next titration case we're going to consider will be if you have a strong base in the burette, okay, and your unknown or analyte is a weak acid, okay, which is in the Erlenmeyer flask. Okay. So let's consider the titration of acetic acid, a weak acid, and it's being titrated with a strong acid NaOH. Okay, so this is NaOH here. Okay, again, there's four regions of interest that we would like to do calculations of and to look at. At the initial pH, similar to the strong acid we considered earlier, HCl, and for that matter, perchloric acid, the pH is at acidic values. However, note that this value is actually higher, slightly higher, not even slightly, but higher, than the pH of hydrochloric acid in the titration curve earlier before any NaOH was added. So that is actually one difference between a weak acid being titrated with a strong base. Okay. Now, similar to the titration of a strong acid with a strong base, we see an increase in pH as more and more strong base is being added into the Erlenmeyer flask. Okay. However, when we are about to hit the equivalence point, notice how the pH change in the rapid rise portion of the curve, which is this area, okay, is smaller for the weak acid than for the strong acid. In other words, it is less steep. Okay. A few things too that you should know. The equivalence point at this region is not at 7 anymore. You are now at a basic pH. And that makes sense because the product of a weak acid plus a strong base is a basic salt. Now, before we forget, looking back at this second region of interest, which is a region wherein we actually have a buffer, one more specific region of interest, in particular for the buffer region, will be the pH at half the equivalence point. At half the equivalence point, the pH of the solution is equal to pKa. In other words, here you have an equal concentration of the weak acid. And remember that when the strong base reacts with a weak acid, you will produce the weak conjugate base of the weak acid, for this case, acetate ions. So here there's an equal concentration of acetic acid and acetate ions. And then going to the right of the equivalence point, again, the equivalence point here is a basic pH. We see that now that acetic acid has been fully consumed, we have an excess of hydroxide ions. Okay. Now, let's say aside from acetic acid, we dilute another monoprotic weak acid. And let's say we have the same volume as this previous chart. We have 25 ml and the same concentration as well, 1.10 molar of another weak acid. Now, the equivalence point, the volume at the equivalence point will still occur at the same volume value, okay? Meaning it doesn't matter whether an acid is, a weak acid is weaker than the other, or for that matter, even if you have a strong acid, as long as it's monoprotic and the same volume and the same concentration, the equivalence point will still occur at the same volume. Now, however, note again that for a strong acid, this steep increase or the sharp change of pH as you are about to hit the equivalence point actually is wider than if you have a weaker acid. Again, this change in pH is actually steeper than if you have a weaker acid being titrated with a strong base. Okay, now it has been observed actually that this equivalence point becomes more and more blurred meaning this sharp change in pH actually becomes less and less pronounced as the pKa value of the weak acid or the acid in general increases. Okay? Or another way to say that, remember that an increase in pKa actually means a decrease in Ka. So the less stronger an acid is, okay, the less stronger an acid is being titrated with a strong base, then this change in equivalence point or that rapid rise at the equivalence point becomes more blurry. Okay. Now, as we have mentioned already before, too, um, weak acids will start with a lower pH at the titration, and we can also observe the same thing too as we increase the pKa values. So the weaker the acid that is, the higher we start with, the higher pH value we start with. Now, this equivalence point rapid rise portion of the graph also becomes more blurred when you are working with two dilute weak acids. Okay, say for example here, the steepest point in the graph will be this black one, which is 20 millimolar of a weak acid HA. Compare that to 0.002 millimolar of this weak acid HA. Okay, so let's work on those four regions of interest again at the titration curve. Let's calculate the pH of the solution of this time acetic acid when it is titrated with KOH at the following volumes of KOH added. So again, this is a solution, or this is a problem in which you are titrating acetic acid, so this is CH3COOH with KOH. Okay, this is a strong base, and acetic acid is a weak acid. Okay, so we begin first with A, wherein we do not add anything from KOH. So at 0 ml of KOH added, the only species present is acetic acid. Okay, only CH3COH is present. Okay, now this is a weak acid, so we have to do an ice table to calculate for the concentration of hydronium ions. So that will be, CH3 COOH, okay, plus water, we're going to yield H3O plus acetate ions, okay, and ICE. Okay, this is a nice table, so we can actually use molarity. So here we write 0.200, that's the initial concentration of acetic acid. Okay, and then we ignore water, this is 0, 0, okay, minus X, this is plus X, and this is plus X, okay, and this one should be 0.200 minus X at equilibrium, okay, and then this will be X at equilibrium for hydronium ions, and X for acetate ions at equilibrium. Okay, and then after that, let's assume that X is a negligible value. That's why we observe that high pH concentrations at the titration curve. But let's see if our assumption works. Let's assume that this is 0.200 molar. Okay, so therefore, let's write the Ka expression. Ka is equal to 1.8 times 10 to the negative 5. Okay, is equal to the concentration of the product, so X times X, okay, divided by the concentration of the reactants at equilibrium. We only have one, so 0.200. All right, and then if we actually solve for X, we're going to get X is equal to H3O plus, okay, is equal to 1.9 times 10 to the negative 3 molar. Okay, and then from there, You can get the pH then by just getting the negative log of the hydronium ion concentration. So pH is equal to negative log of 1.9 times 10 to the negative 3. Okay, and that should be equal to 2.72. Okay, I am not going to do the 5% rule here again anymore, but if you want to try that out on your own, you will actually notice that this assumption is valid. But note at how high this pH is compared to a strong acid, strong base pre-titration setup. Okay, so here the pH is higher by a decent magnitude. Okay, let's work now with B. What if we add 50.00 ml of potassium hydroxide? Okay, so for this one, remember that KOH is a strong base, so it will dissociate into potassium plus and hydroxide ions. The hydroxide ions will be the only one which is basic. Potassium ions will have no acidic or basic properties. So here, hydroxide will completely react with, well, acetic acid. And that reaction can be written in an ICF table as follows. So millimoles, okay, and then the reaction is we have acetic acid plus hydroxide ions going to form acetic ions, okay, plus water. Okay. So since this is millimoles, let's calculate for the millimoles of each of these components. So for acetic acid, that should be 100.0 ml times 0.200 molar. So that should just give you 20.0 millimolar. Okay. For hydroxide, this is 50.00 ml times 0.100 molar. This is just going to be equal to 5.00. Okay, we do not start with any acetate ion concentration or millimole, and then let's just assume water is also equal to 0, but we're not gonna put it in our calculations anyway. The limiting reagent here will be OH. Okay, so it's fully consumed. So we subtract from 25.00. This one should be 5 minus 5.00, and then we produce acetate ions and more water. Okay, so that in the end we will have 15 millimolar of acetic acid left. We have none of the hydroxide ions, and then we have 5 millimolar or millimoles rather of acetate ions. Okay, and then the next thing that we want to do here is since we have a buffer, okay, since we have a buffer, we have the concentration or we have the number of millimoles of acetic acid. We have the number of millimoles of acetate ions. We have a total volume of the solution. We can determine therefore what the pH of the solution is from the Henderson-Hasselbalch equation. Okay, remember that the form of the Henderson-Hasselbalch equation we're using is pH is equal to pKa plus log of, for this time, base over acid, so this is concentration or molarity of acetate ions divided by, divided by the concentration of acetic acid. Okay, so let's plug in these numbers. So pH should therefore be equal to negative log of 1.8 times 10 to the negative 5. Okay, and then this should be plus log of let's solve for concentration of acetate ions, but let's not determine the molarity but instead plug in the numbers. Okay, so that will be for acetate ions 5.0 millimoles divided by 100.0 plus 50.00 ml. Alright, and then divided by for the acid 15.0 millimoles divided by 100.0 plus 50.00 ml. All right. So again, as you can see, the total volume of the solution is, well, the same for both cases anyway, for both acid and base. So this will cancel out, and it looks like for the Henderson-Hasselbalch equation, at least for titration, we can work with millimoles. So let's actually remember this rule when we solve for the other points of the titration curve. But anyway, this one becomes the negative log of 1.85, or 1.8 times 10 to the negative 5 is 4.74. Let's remember that number as well. Okay, and that will be, we will end up with log of 5.00 divided by 15.0. Okay, note that millimole cancels out as well, but not the numbers. Okay, and then we will end up with 4.74 plus negative 0.48. Okay, and this will give you 4.26. Okay, so let's compare the pH with the pKa. So this is the pKa, okay, 4.74, and this is the pH, okay, and this is the pH. Notice that for this case, the pH of the solution is lower than the pKa. So pH is lower than the pKa. And if you listen to that video that I uploaded previously, this is a situation in which the concentration of the acid, okay, in this case, acetic acid, is actually greater than the concentration of the conjugate base, which is here acetate ions. All right, let's go to the next problem, letter C. What if we had an addition of 100.00 ml of KOH? Okay. Now, again, we will need an ICF table for this one. So millimoles CH3COOH plus OH minus going to give you acetate ions plus water. Okay. So similar to the first titration case, we're going to start from scratch here for acetic acid. We're not going to begin with 15, okay? Instead, we're going to start with 20, okay? As if this were basically a separate addition, okay? So this one will be separate addition and a separate flask, that is. So this one will begin with 20.0, okay? The OH that we're adding here, the millimoles, will be 100.00 ml, okay, times 0.100 molar is equal to 10.0, okay, and then this one will be 0, 0, okay. Hydroxide is still the limiting reagent, so minus 10, okay, minus 10, and then plus 10, plus 10, this will be 10, this will be 0, this will be 10, there we go. Okay, so we can then calculate for pH. Okay, we know pKa already, so we'll just write pH is equal to 4.74. This again was calculated from the previous slide. Okay, and then that will be plus log of, we established earlier here that we can proxy millimoles for the concentration. Okay, using this argument that we have derived here. Okay, so that's going to be log of 10.0 millimoles of sodium acetate, or acetate rather, and then divided by 10.0 millimoles of acetic acid. Okay, notice that this ratio is equal to 1. The log of 1 is equal to 0, so this one actually cancels out. So this is a case in which we actually have pH is equal to pKa, which is 4.74. So this is actually the point at which we are half the equivalence point. Okay? At half the equivalence point, again, pH is equal to pKa, And at half the equivalence point, since pH is equal to pKa, that just means that the concentration of acetic acid in solution is equal to the concentration of acetate ions. Okay, let's go next to letter D. What if we have a total of 150.00 ml of KOH added? Okay, so for this one, again, the KOH will still consume acetic acid. So another ICF table, the same thing actually. So millimoles and then CH3COOH. Okay. And then okay, we begin again with 20.0 millimoles of acetic acid. Okay, for hydroxide, we have 150.00 ml. Okay, times 0.100 molar. That will give us 15.0 millimoles. Okay, and then 0 of the acetate ions. So still hydroxide here is the limiting reagent, so this will be minus 15.0 minus 15.0. This will be plus 15. Okay, and then in the end we will get 5.0 for the millimoles of acetic acid, nothing left of the hydroxide, and then we have 15 here for acetate ions. Okay, and this one will be 15 as well, but we don't really care about, well, this is not OH minus, sorry, this is water. Okay, so after that we calculate for the pH. pH is equal to 4.74 plus log of 15.0 millimoles divided by 5.0 millimoles. Okay, that one should give you 4.74 plus 0.48, which is equal to 5.22. Okay, notice that at this point pH is greater than pKa. Okay, and this is a scenario in which the concentration of the acidic component, the weak acid, acetic acid, is less than the concentration of the acetate ions. Alright, let's move forward with letter E. What if we have added 200 ml of potassium hydroxide? So again, let us write an ICF table. Okay, I'm writing small because we have a lot to write in this page. Okay, so CH3 COOH CH3 CO minus plus H2. Okay. All right. So here we begin again with 20.0 millimoles of acetic acid. Okay. This time for hydroxide ions we have 200.0 ml or 200.00 ml rather. Times the molarity, which is 0.100 molar. Okay, so that's equal to 20. And then this one should be 0 and 0. Notice that we have equimolar amounts of acetic acid and OH. They will fully consume each other. So we are actually at the equivalence point. Okay, so this is minus 20.0 minus 20.0. This is plus 20.0. And in the end, we will have none of the acetic acid left, none of the hydroxide present, but we have converted all of the acetic acid into acetate ions, 20.0. Okay, so since we have acetate ions here as the dominant species in the solution, to calculate for the pH, we first need to know the hydronium ion concentration that it will produce when it is in equilibrium with water. And to do that, we have to write an ice table, considering again the hydrolysis of acetate ions. So that one should just be, the hydrolysis reaction should be CH3, COO minus, okay, with water, in equilibrium with acetic acid, okay, plus OH minus. And if we write a nice table, there should be molarity, initial, concentration, change, equilibrium. So here we have 20 millimoles of acetate ions. Since we're calculating for molarity, we have to divide the 20.0 millimoles with the total volume now of the solution, which at this point is 100 ml of acetic acid plus 200 ml of KOH. Okay, so it's 300 ml. So 100.0 plus 200.00 ml. Okay, so this should just give you a concentration of 0.0667 molar. Okay, ignore water. Then we have zero concentration of acetic acid and no OH as well. Okay, and then from there, the change will be minus X plus ignore plus X. Okay, and this will be plus X. So that we have at equilibrium 0.0667 minus X. Okay, X and then X. Okay. We can then set up an expression for Kb. First, we assume that that X is negligible. Okay, so that the concentration of acetate ions at equilibrium doesn't really change. So the Kb for this one is, we're not given the Ka or the Kb of acetate ions, but we're given the Ka of acetic acid. So we can calculate from there what the Kb is. So that should be 1.0 times 10 to the negative 14, okay, divided by 1.8 times 10 to the negative 5, okay, should be equal to, the equilibrium expression should therefore be equal to X, okay, times X, okay, divided by 0.0667, okay, and then this further simplifies into 5.6 times 10 to the negative 10, okay, equal to X squared divided by 0.0667. Further simplifying this equation, we have 3.7 times 10 to the negative 11 is equal to X squared. And then we have X is equal to 6.1 times 10 to the negative 6 molar. Remember that this is the concentration of hydroxide ions. See how far or how small this number is compared to 0.0667. That means that our assumptions are good. Okay, you can do the 5% rule as well. I'm not. But the pOH of the solution should be the negative log of 6.1 times 10 to the negative 6 molar. We can get the pOH from the hydroxide ion concentration value. This will be equal to 5.21, and therefore the pH of the solution should be 14 minus 5.21 is equal to 8.79. Okay, so at this point, if you're doubting this value, check. At the equivalence point here, you should only have acetate ions in solution present. Okay, so since acetate ions are basic, then the pH should indeed be basic. And then lastly, for the last we consider what the pH of the solution is after an addition of 250.00 ml of KOH. So we are now past the equivalence point. So doesn't matter. Let's start with again an ICF table in which we're considering the reaction of acetic acid, CH3COOH, with hydroxide from KOH that will produce acetate ions plus H2O. Okay. All right. So again, acetic acid has 20.0 millimoles. Okay. For hydroxide, that's 250.00 ml times 0.100 molar. This should give you 25.0. And then we begin with no acetate ions. Okay. This time now, look that acetic acid is now the limiting reagent. So this one's minus 20. This is minus 20.20. This is plus 20. Okay. And then this one's also plus 20. Okay. So then we'll have 5.0 millimolar of hydroxide. We have 20.0 millimolar of acetate ions as well. Now, at past the equivalence point, we have two species which can actually determine the pH of the solution, OH and acetate ions. However, we assume that the amount of hydroxide added from the weak base is very minimal. Okay, as proof of that, in the previous calculation, apparently it's not there anymore. We note that there's a low concentration of acetate ions being produced. Okay, so pH is just going to be a function of this millimoles of OH. Okay, of the excess OH, that is. So here, therefore, the pOH of the solution should be equal to negative log of, let's calculate the concentration of this excess OH minus. So that's 5.0 millimoles divided by the total volume, which is 100.0 plus 250.0 ml. This will just give you negative log of 0.014 molar. And that should be 1.85. And finally, to solve for pH, pH is just 14 minus 1.85. That's equal to 12.15. All right.